Hello everybody, and welcome to the beginning of section 1.2. We are looking at page 8 in the workbook, and we are about to talk about what is probably the most important definition of our course, the idea of a vector space. Okay, what is a vector space? Well, basically it's just a collection of things that we're going to call vectors that follows a list of rules. Okay, so let's take a minute to read this definition together. So a vector space V over a field F, okay, and this term field is just a word for the set of scalars, okay? So when you see F in this book, think of it as either the set of real numbers or the set of complex numbers, just scalars that we can multiply by. Okay, and to be a vector space, we'd like to have two operations that we can perform on our vectors. The first one is vector addition. For each x and y in V, we'd like to be able to add x and y together and get a new vector in our vector space. This property is called closure under addition. Okay, and then one other operation that we'd like to be able to do is to take a scalar from our field and multiply it by a vector. So for each x in V and scalar a in our field, we'd like to be able to take a times x and get another vector. Okay, and this is called closure under scalar multiplication. Okay, so far, a vector space is just a collection of vectors with two operations, addition and scalar multiplication, and the last part of the definition is we want our addition and scalar multiplication to satisfy a set of rules. And that's these 8 rules, VS1 through VS8, that you see down here on this list. Okay, and we won't talk through every one of these rules, but I would like to highlight a couple of the more important ones here. Okay, so maybe starting with the first one. So VS1 says, for all x, y, and v, x plus y equals y plus x. We gave a name to that property, I think in the last section. So this would be called commutativity of vector addition. Okay, what about VS2? For all x, y, and z in V, x plus y grouped together plus z is x plus y plus z grouped together. Do you remember what the name for that property is? And that would be associativity of vector addition. Okay, and then we come down to VS3 here. Let's read that one together. There exists an element in V denoted by 0 such that x plus 0 equals x for all x in V. Okay, that 0 there is what's called the zero vector. It's just there, we want to have a vector that we can add to any other vector and get that same vector back again. So it behaves like the real number 0 does. Okay, now there's a little bit of a notational point that I want to make here. Let's clear some space for ourselves here. If you look really carefully at this 0, you might notice that it's italicized. Okay, that's the notation that our book has chosen to help us distinguish between the scalar 0 and the vector 0. But when we're writing by hand, it's really difficult to tell the difference between an italicized 0 and a normal 0. And so when I write the 0 vector by hand, here's how I'll probably do it. I'm going to write 0 with a little v, and you should think 0 vector when you see that notation. Okay, the little v is just a way of saying that's the 0 vector and not the scalar 0. Okay, and one more property that we'll just talk through together here. For each x in V, there exists a y in V such that x plus y equals 0. Okay, this is just a way of saying that each vector in our vector space has a negative, another vector that we can add to it that gives us back to the 0 vector. Okay, and we'll use this notation, negative x, for the additive inverse of x. Okay, and I'll leave it to you to read the rest of these properties. But in a nutshell, kind of just looking at this definition from top to bottom, a vector space is just a set of vectors where we have two operations, vector addition and scalar multiplication, and such that those operations satisfy these 8 properties. And in future videos, we'll look at some examples of vector spaces.